Ever wondered how a 200,000-ton ship can literally climb a hill of water and then descend back down to the ocean on the other side? Today on Knowledge Hub, we're breaking down the engineering genius behind the Panama Canal, the waterway that connects the Atlantic Ocean and the Pacific Ocean, even though they sit at different sea levels and are separated by mountainous terrain. Unlike the Suez Canal, which runs at sea level, the Panama Canal is a lock-based canal, meaning ships are lifted approximately 26 meters above sea level to cross the Isthmus of Panama via the artificial Gatun Lake. But here's the fascinating part. The two oceans aren't perfectly aligned in height at this location, and the Pacific side also experiences much larger tidal variations than the Atlantic. Add in the continental divide, solid rock and jungle-covered hills, and carving a sea-level passage in the early 1900s would have been nearly impossible. So engineers designed a gravity-powered hydraulic elevator system instead. When a ship enters the Gatun locks on the Atlantic side, massive steel miter gates close behind it. These gates, some weighing over 700 tons, seal the chamber. Then, using a network of culverts embedded in the concrete walls and floor, fresh water from Gatun Lake flows in purely by gravity. No pumps, no mechanical lifting arms, just hydrostatic pressure and controlled valve systems. As water fills the chamber, buoyant force increases and the ship rises with the water level. This happens in 3 sequential lock chambers, each raising the vessel about 8 to 9 meters, until it reaches the elevation of Gatun Lake. The ship then travels across the lake and through the Galliard Cut, a man-made valley carved through the continental divide, before descending on the Pacific side via the Pedro Miguel and Miraflores locks. Each lowering stage works in reverse. Water is drained into lower chambers or out toward the ocean, and gravity gently lowers the ship. A complete transit takes around 8 to 10 hours. Each passage through the original locks consumes roughly 190 million liters of fresh water, which ultimately flows into the sea. That's why rainfall is critical to the canal's operation. In fact, during drought years, transit capacity must sometimes be reduced due to lower lake levels. In 2016, a massive expansion introduced the new Neopanamax locks, allowing significantly larger vessels to pass. These newer locks use rolling gates instead of traditional miter gates and incorporate water-saving basins that recycle about 60% of the water used in each lock cycle, a major advancement in sustainable hydraulic engineering. Structurally, the locks are reinforced concrete monoliths designed to withstand immense hydrostatic loads. Precision control systems manage water flow rates to minimize turbulence, preventing dangerous ship movement inside the chambers. Tugboats and locomotives, often called mules, guide vessels to keep them perfectly center. So when a ship crosses from the Atlantic to the Pacific, it doesn't simply sail across at sea level. It is raised, transported across a man-made freshwater lake, and then lowered back down, all powered by gravity, fluid mechanics, structural engineering, and over a century of innovation. So the next time you see a cargo ship floating higher than the ocean itself, remember, it's not defying physics, it's mastering it. The Panama Canal isn't just a shortcut between two seas. It's a controlled water staircase that moves nearly 5% of global maritime trade and reshaped international commerce forever. If you enjoyed this deep dive into one of the world's greatest engineering systems, make sure to subscribe to Knowledge Hub for more breakdowns of how the world really works. And as always, stay curious.